Okay, this is 2011, Form B. So this is a Taylor Series 1. It asks you for Part A to actually tells you, which is a little odd to me, that they actually tell you the natural log. 1 plus x is this. So they tell you the Maclaurin series for the natural log, and then they just want you to use it to rewrite the natural log of 1 plus x cubed, which to me sounds like they didn't have to do that. They could have just made you write this out from the get-go. So again, they tell you this is x minus x squared over 2. I would expect you to have this memorized. Again, surprised when they do stuff like this. Alternating version of x to the n over n. And again, they say use this to write this guy. Again, that's just putting in x cubed wherever you see that. So that would mean x cubed. This is going to be minus x to the 6th over 2 plus x to the 9th over 3 minus x to the 12th over 4 plus dot dot dot. Still alternating, except now it's x cubed to the n, which is x to the 3n over n. Okay, that was easy. That was the first two terms. Okay, part B says find the interval of convergence. Okay, so the interval of convergence, remember we can write this as a Riemann sum of -1 to the n, x to the 3n over n. So if you look at if you do the ratio test, I'm not even sure you need to do the ratio test. You know this is going to be -1 to 1 because you know what a logarithm is. It's derived from the geometric series. You can do the ratio test, but you know that this thing has to be between that. So this is 3 to the n plus 1 over n plus 1 all over -1 to the n, x to the 3n over n. If you do the ratio, oops, I always forget to write this, but when you do the ratio test, you always look at the limit as n goes to infinity. This goes away, this goes away. That just creates a -1, but we don't even care about that. That's 3x to the 3n plus 3 over x to the 3n, and so you get x cubed. You set that between -1 and 1. That's the same thing as just setting x between -1 and 1. So again, whether you had to do that or not, I'm not really sure, but we knew this had to be the case. The ratio test proves that for us, and now we need to look at the endpoints. Okay, looking at the endpoints on these, I actually think this is kind of tricky sometimes when you look at, well, what happens when you plug a -1 in here, but this is already -1. I would encourage you to just come up here and look at this. Okay, if x is equal to 1, well, x is equal to 1 is the easy one. If x is equal to 1, that just goes away. So if x is equal to 1, you are just looking at the alternating series 1 over n. And again, we know this converges, and so yes, include 1. If x is equal to -1, what happens? Well, if x is equal to -1, I think this is easier to look at. If x is -1, that's negative, 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 negative. Do you see how the normal series alternates? And if you plug in -1 for x, you're going to turn all these positive ones that are odd all negative. The even ones will stay negative, and so you'll actually get the negative version, just always negative version of 1 over n, which doesn't converge, right? That's just, there's no n there. This is not a non-alternating series. These are just all negative numbers. And so we don't want to include -1, and so that is our interval. Again, you must look at the endpoints, however you want to approach that, but you need to look at the endpoints and decide what series they actually give you, and that's different. Again, 1 is an alternating version. This doesn't give, this is just the negative version of all of those things. Okay? Part C, pretty in depth on part C. Part C says, right, the first 4 non-zero terms for f prime of t squared. F prime of t squared. Okay, so here's f. So let's just find f prime. F prime of x is me taking this derivative. Okay, so just take these derivatives. So that's 3x squared minus, I bring that 6 down, that's going to be 3x to the 5th bring that 9 down, plus 3x to the 8th, bring that 12 down, minus 3x to the 11th, plus dot, dot, dot. Alternating version, if I bring this down, I get 3n to the x, 3n minus 1 over n, those n's cancel. All right, that's f prime. This one's kind of silly. Then I want f prime of t squared. All right, that's just me plugging in t squared for x. So that's 3t to the 4th minus 3t to the 10th plus 3t to the 16th. I guess I can keep going here. Minus 3t to the 22nd plus dot, dot, dot. Alternating version of 3 t squared to that, so that's t to the 6n minus 2. I'm just putting a t squared in for x. All right, so I did that. And now g, they define g as the integral of f prime of t squared. All right, so let's find g, which means to just integrate this silly thing. So I just get 3/5 t to the 5th minus 3/10 t to the 11th plus 3, my bad, that is 11 there. Increase the power by 1 and divide by the new power. Okay, and I could keep going, right? Minus 3 over 23 t to the 23rd plus dot, 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 dot. Do I actually need to do that? No. All it says is use the first two non-zero terms of g. Okay, so those are the first two non-zero terms of g to approximate g of 1. Okay, so then if I use those two terms of g of 1, I put 1 in for t, then I get 3/5 minus 3/11. Okay, do a little algebra there. That is going to be 33 over 55 minus 15 over 55, which gives me 18 over 55. Okay, that's g of 1. Okay, part C is done now. That was kind of convoluted, but if I have f, I can find f prime, which means I can find f prime of t squared, and then I can find g, where they define g as the integral of f prime of t squared. I just integrate all of those things. Then it said use the first two terms to approximate g of 1. So the first two terms and plug in 1 for t and get this silly thing. And then part D says, I'm going to put that down here, that's the hard one to read. This is the error one. The Maclaurin series for g evaluated at 1 is a convergent alternating series. So it's telling you, hey man, I'm an alternating series. So that means that the error is just the next term that I didn't use. And show that my approximate error is less than 1/5. Okay, so up here, look. If I use these two terms, this guy is my error. That term evaluated when t is 1 is 3 over 17. Bingo. I just showed you that the error is less than 1/5. This is less than 1/5. 1/5 is 3/15. 3/17 is smaller. Again, you want to show that since it's an alternating series, that the approximation must differ from g of 1 by less than this. That is just shouting at you, show me that the error is less than 1/5. I go down here, I find that the error is the next term. I show that that thing is less than 1/5 at t equals 1. Okay?